Okay, welcome to Math 355 Abstract Algebra. This is lecture 22. So we are starting our third pass on groups. And so today we're going to be talking about permutation groups, cycles, and a little bit maybe at the very end on solvable groups. This is also the time of year where we are looking at what classes, for those of you who are not graduating, you might be interested in taking next year. So I wanted to spend the first moment of class today talking about one of my favorite riddles, and then I will have you think about this. Do not look online. You can talk to friends, but you cannot look online about this. So I will be teaching a class in the fall next year called The Little Questions on Problem Solving. And the goal of that class is not really content, but how do you approach problems? So here's the riddle. You have 100 numbered prisoners, numbered 1 to 100, and let's assume that they are mathematicians, so they're extremely intelligent. They're allowed to strategize beforehand, but they come into the room one at a time, and after they strategize, they cannot communicate with each other. And each one can open up to 50 cabinet drawers. And if they see their number, then that counts as a win. If they don't see the number, it counts as a loss. Everybody must see their number. Everybody can open at most 50. If even one person doesn't see their number, they lose, and we'll say they all are killed, because we can be violent because this is just hypothetical. If they all see their number, they are all paroled. And so the question is, what is the best strategy? And again, they can't leave drawers open. They can't leave clues or hints for everybody else. Everyone must find their number for the team to win. If you just look at what happens for one prisoner, if the prisoner just randomly opens 50 out of 100 cabinets, the probability that they see there is, given that there's 100 possibilities, is 50 over 100 or 1/2. If the prisoners are all acting independently, the probability that they are all correct is 1/2 to the 100. So when you have 1/2 to the 100, you can actually approximate this pretty well in your head. 1/2 to the 10th, well, 2 to the 10th is 10 cubed, is 1,000, roughly. So 1 over 2 to the 100 is roughly 1 over 10 cubed to the 10th, or about 1 over 10 to the 30th. So the probability, if they all guess randomly, that they survive is about 1 over 10 to the 30th. Can you do better? And so that's your challenge for Thursday. Again, you can't look this up online. Can you come up with a better strategy that has a higher chance of winning than this? All right. So now swinging back to abstract algebra, what we're going to do today is we're going to talk about permutation groups and different ways to decompose them and why we might care about stuff like this. So if you've played any games with cards, does anybody know the 4 suits of a standard deck of cards? Yes. Now, we normally say spades, hearts, diamonds, clubs, at least if you play bridge, because that is a natural ordering of the suits. So a spade bid is a higher than a heart bid, but there's 4 suits. We could call the suits, if we wanted to, carrots, cucumbers, celery, and I need another vegetable that begins with a C. Corn is technically not a vegetable. I'll use corn, right? Does it matter if I call them carrots, cucumbers, celery, and corn and use those as my symbols? No. And so because it doesn't really matter, we frequently use 1, 2, 3, all the way up to n to denote the elements of the set that we're permuting. And we look at the set of all permutations of these objects. And so if we have n elements, the number of possible permutations is n factorial. So the first question we're concerned with is how quickly does the size of the permutation group grow? So we know that the size of Sn is n factorial. And we want to estimate how big is that? Well, if you have taken any class with me before, one of the things you know is I love a Pavlovian response when you see a product. Whenever you see a product, you should take a logarithm. If you are teaching multiplication to 4th graders, okay, resist the temptation there. But otherwise, in upper level math classes, if you see a product, take a logarithm. The reason is we have familiarity with sums. There's really no difference. If I exponentiate a sum, I get a product. But we have familiarity with sums. So the log of n factorial is the log of 1 plus the log of 2 plus ... plus the log of n. How could you approximate the sum of logarithms? So how would you approximate the sum of logarithms? What previous class can you use? So one of the things you have to do in mathematics is you have to not just have facts at your disposal, you have to know which facts are useful and when. If I wrote this as the log of 1 times 1 plus the log of 2 times 1 plus dot 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 plus the log of n times 1, does this make it a little bit easier to think of how I might be doing things? Does this remind you of anything? So this should remind you of a Riemann sum. This is like the integral from 1 to n of the log of t dt. I'm not going to worry about getting the endpoints right and everything, but I'm just trying to get rough order of magnitude. But basically, I've got some long interval of size n. I'm dividing it into spots of size 1. If I give you any function built up of sines, cosines, tangents, exponentials, polynomials, can you find its derivative? Yes, I cannot stump you even if I want to. You just keep using the laws of differentiation. If it's a product, use the product rule. If it's a composition, use the chain rule. And you can just keep applying this. It is inexcusable to get a derivative wrong. What about an integral? Is it okay to get an integral wrong? That's not what I'm asking. I'm not asking, is it inexcusable to be unable to integrate? I'm asking, is it inexcusable to have the wrong answer for an integral? Right. And so if you claim that you have an integral, what can you do to see if you're right? Differentiate. So it is inexcusable to give me the wrong integral for something. It's excusable not to know how to integrate it. This is the big lie of Calc 2. You leave Calc 2 thinking you know how to differentiate, you don't. Most integrals cannot be done in closed form. This one can. It's a nice problem. It turns out the antiderivative of this is t log t minus t. So we evaluate that at 1 and n, and we get n log n minus 1 log 1 minus 1. And so we get that the log of n factorial is approximately n log n minus n, or n factorial is approximately e to the n log n minus 1, which is n to the n e to the minus n. So the log of n factorial, we can estimate it pretty well. I can do a better job than this. I'm just trying to get rough order of magnitude. This is the integral test from calculus. You should hopefully have seen something like this a while ago. This group is growing very rapidly in terms of how many elements there are. So the next is proposition 12.3. The group Sn has n factorial elements. Okay, we've talked about that. The more interesting one is for all n greater than or equal to 3, the group Sn is non-abelian. What do you think is true if n equals 1 or 2? It's probably abelian the way it's stated, right? I could, of course, been tricky. I could have said for all n greater than or equal to 17, the group Sn is non-abelian, and been nasty and implied that maybe it's not that way for n equals 1 or 2. Let's do the calculation. So let's do n equals 1 and n equals 2 separately. If n equals 1, then S1 is just the identity element E. Clearly abelian. If n equals 2, then S2 has just 2 elements E, and the transposition that sends 1, 2 to 2, 1. there's no other possible permutation. I either don't change anything, or I send 1 to 2, at which point I have to send 2 to 1. In order to have something that's non-abelian, I have to have 2 distinct elements and multiply them, and the order has to matter. Well, my group at least has 2 distinct elements, so I have a chance of being non-abelian, but one of the elements is the identity. And the identity commutes with everything. So clearly, this has to be abelian. I only have to check distinct multiplications, and I don't have a distinct multiplication unless I involve the identity. So things start to get interesting when n equals 3. And so if I can show that S3 is not abelian, I can actually extend that upwards. And what I'm going to do is I'm going to look at 2 different elements. And I'm going to send, 4, 5, 6, all the way up to n to itself. Because if I can find an example like this, then by showing that S3 is non-abelian, then I'll get all the SNs with n at least 3 are non-abelian. If I can find one example where I don't change what 4 goes to 5 goes to 6 goes to, if I leave them alone. So now, there aren't that many possibilities. How many elements does S3 have? 6, but one of them is the identity. So there's 5 elements. I have to choose 2 distinct elements. How many ways are there to choose 2 distinct elements from 5? 10. So there's really only 10 multiplications to do. Now, I do know at least one person has emailed me recently about all the different multiplications that they might have to do to factor some polynomials or to see that a polynomial can't factor. So is there a thought process we can do to try to cut down on the multiplications? Well, we know that if there's a chance to be non-abelian, one of the elements we take, it can't be the identity. So I can't send 1 to 1, 2 to 2, 3 to 3. At least one element has to be sent to something else. So without loss of generality, I might as well send 1 to 1. Right? I'm sorry, not 1 to 1, I'm sorry. I might as well send 1 to 2. Without loss of generality, at least one element not sent to itself. So once I send 1 to 2, how many possibilities are there for what 2 gets sent to? Where can 2 go to? So I have 2 possibilities. Either 2 goes to 3, in which case I have a cycle, or 2 goes to 1 and 3 is left alone. Let me try sending 2 to 1, and then keeping 3 to itself. So this is just a transposition. It just flips 1 and 2. And so we denote that by tau 1, 2. On the other side, I want to try to figure out what's going on. And I have a lot of different possibilities. Before I sent 1 to 2, what might be a good thing to try now? Let's send 1 to 3. And I can try to keep things simple. Maybe I'll send 2 to 2, and I'll send 3 to 1. And this will give me tau 1, 3. And again, I hope you see that these are natural things to try in terms of trying to find an example of a multiplication that's not commutative. I didn't have that many choices for the first. I really only had 2 possibilities. I send 1 to 2, and after that, I either send 2 to 1 or I send 2 to 3. For the next one, I actually have more possibilities. All right, let's see if this works. So I've got my 2 different products. I have tau 1, 2, tau 1, 3, and then tau 1, 3, tau 1, 2. And you always do it inside or inner than outer. You start on the far right and you move outward in terms of how you're doing the multiplication. So I only have to worry about what it does to 1, 2, 3. So I want to figure out what the impact of these are going to be. So tau 1, 3 sends 1 to 3, 2 to 2, 3 to 1. So I'll put that in my two places. And then tau 1, 2 sends 1 to 2, 2 to 1, and leaves 3 untouched. And now let's see what they each do. So for the first one, I send 1 to 3, and then 3 goes to 3. So I know it starts off with 1 goes to 3. Again, I am trying to illustrate today one of the fundamental attributes of a good mathematician: laziness. I want to do as little work as necessary. Should I continue multiplying the stuff on the top, or should I start multiplying things on the bottom? Which should I do next? Good. I should go to the bottom, because as soon as I find something on the bottom that is not the same as something on the top, I'm done. I don't have to finish the calculation. Well, if I look at the bottom, 1 goes to 2, 2 goes to 2. So this is already enough to show not the same. So not abelian. And again, I could have done the full multiplications and I could have calculated what they actually are. But since I'm only concerned about showing that they're not abelian, this was enough. Okay, any questions on this? And again, what I care most about this proof is the thought process, is how did we come to do as few calculations as possible to see something like this? How did we find good candidates to look at? All right, so the next one is, suppose we have a permutation, then we can look at essentially what's going to happen with the orbits. So if we go back to the previous problem, I could take, I've got my tau 1, 2 and my tau 1, 3, and I can see what do they do. So what would tau of 1, 2, what would that send 1 to? It would send 2. And then what would tau 1, 2 of tau 1, 2 of 1 equal? So that's, tau 1 squared, I'm sorry, 1, 2 squared of 1. It would be back to 1. And we would get tau 1, 2 of 3 would just be 3. So we could write, tau 1, 2 as a nice orbit like this. And more generally, let's say we have the permutation 1, 2, 3, 4, 5, 2, 3, 1, 5, 4. I claim we can write this as 2 different permutations, but we can look at orbits. So if we call this pi, what would pi of 1 be? That would be 2. What would pi squared of 2 be? I mean, pi squared of 1 be? 3. What would pi cubed of 1 be? 1. So we get 1 goes to 2, goes to 3, goes back to 1. Do I need to look at what pi of 2 is? Do I need to start calculating what pi of 2 is? No, I already know from over here. Do I need to calculate pi of 3? No, I already know from over here. What about pi of 4? So if I want to look at pi of 4, that would be 5. Pi squared of 4 would be 4 again. So 4 would go to 5 would go to 4. And this allows me to write this cycle as 1, 2, 3 goes to 2, 3, 1, and then 4, 5, 5, 4. Or could I write it as 4, 5 goes to 5, 4, and then 1, 2, 3 goes to 2, 3, 1? Can I write them in different orders? What do you think? Why? Yeah, equal as disjoint. I don't have any numbers in common. So what the 4 and the 5 do is they mix up the 4s and the 5s. They don't have any impact on the 1, 2, 3s. So it doesn't matter which order I apply the stuff. So the big result is that you give me any permutation, and I can write it uniquely as a product of cycles. If I put in some additional constraints. And so here, we want the cycles to be disjoint, but I can always reorder them as to which one is first, which one is second, which one is third. If you don't like that, you could always say, for each cycle, order it so that the smallest element in the cycle comes first. So for the cycle 1, 2, 3, I'm going to have it starting off with what 1 does. And then if I have multiple cycles, whichever cycle has the smallest element, that I'll list first. Then whichever one has the next smallest element, I could list second. I could do something like that if I really wanted uniqueness. This is not so bad. Is look at the action of pi on 1, 2, ... n. It breaks into distinct orbits. So for example, and this is going to be proof by example, let's say 1 goes to 3, goes to 7, goes to 18, goes to 9, goes to 6, goes to 1. So I look at all of the applications of pi to 1, to pi of 1, to pi squared of 1, and so on and so on and so on. And that's going to give me my first cycle. What's the next number I should look at? 2. 2 is not on my list. So let's say maybe 2 goes to 8, goes to 16, goes to 31, goes to 2024, goes to 6, goes to 9, let's see, goes to 11, goes to 1. Is this a possibility? I have 6 twice. I can't do this. I've already got 6 in one orbit. I can't have 6 in 2 orbits because in the first one I have 6 going to 1, here I have 6 going to 11. I'm sorry, that should have been a 2 at the end, not a 1. So this would be illegal. What I could do is I could have 2 goes to 8, goes to 16, goes to 31, goes to 20, 24, goes to 11, goes to 2. That would be okay. What's the next number I should look at? Yes, and so what's the smallest number that's not on my list? 4. And so maybe 4 goes to 4. And then maybe 5 goes to 17 goes to 5. And so on and so on and so on. And so if I were to write this down into cycle notation, I would have 1 goes to 3, 3 goes to 7, 7 goes to 18, 18 goes to 9, 9 goes to 6, and then 6 goes to 1. And then the next cycle would be 2 goes to 8, 8 goes to 16, 16 goes to 31, 31 goes to 20, 24, 20, 24 goes to 11, 11 goes to 2. The next one would be 4 goes to 4. Would I even write that? Probably wouldn't even bother writing that, right? Because that's just 4 goes to 4. That's just the identity. I could do that if I want to have everything counted. You can choose whether or not you want to do that. And so this is essentially a constructive proof that if you give me any permutation, I can write it as a product of disjoint cycles, and I just look at the orbit of each element. And for each element, I calculate its orbit, and then I take the smallest number that's not in any of the orbits, and I look at what happens to that, and I just keep going, going, going Okay. So if I give you the specific example, if I wanted to write this down, go through it. See. So 1 goes to 3, 3 goes to 7, 7 goes to 4, 4 goes to 2, and then 2 goes to 1. So the first cycle would have length 5. The smallest thing that I haven't done yet, I've got 1, 2, 3, 4, so I would look at 5. 5 goes to 10, 10 goes to 8, 8 goes to 5. I now look at what's next. I've got 1, 2, 3, 4, 5. I don't have 6, so 6 would be next. 6 goes to 9, 9 goes to 6, and that would be everything. And this is a nice way to decompose a product. I'm sorry, to decompose a permutation into a product of cycles. I could do them in other orders. I can rearrange these any way I want. This is perfectly fine. So the next, and we've seen this already, an element pi is called a transposition if there are distinct A and B, such that pi of A is B, pi of B is A, and everything else is left alone. So we just switch A and B. So we often denote this by, by tau of AB, and if I wanted to write it, it would be A goes to B and B goes to A. So in some sense, these are the simplest permutations to look at that are non-trivial. The simplest permutation is the identity. The next simplest is I flip 2 elements and nothing else. Is a transposition a cycle? Well, what if you have n things? Is it a cycle? Yeah, because I mean, we're talking about writing a permutation as a product of cycles. This is just a cycle of length 2. So it is a cycle of length 2. It is the smallest non-trivial cycle you can look at. So we just proved that every permutation can be written as a product of cycles. It would be wonderful if instead of using cycles, we could just use transpositions. Now, a product of cycles has some nice properties. When we write things as a product of cycles, the different blocks are independent from each other. If we try to write it as a product of transpositions, we may no longer have that. But it's sometimes more convenient to try to take a complicated object and break it down and write it into something involving simpler things. And so the big theorem is that, given any permutation, I can write it as a product. This does not say that the product is unique. And so we might be concerned later with, is there more than one way to do this? And if so, what different properties will they have? Have you all used Google Maps or Apple Maps or MapQuest or something like that at one point in your life to find how to get from point A to point B? So a lot of times these programs give you multiple choices. What could be a difference between some of the routes? So one could be, some people do not like driving on the highway, so it could be avoiding highways. What else could a difference be? It could, but I'm saying, let's say it's giving you good directions. I have definitely had situations where it has given me wrong directions. But do you want to avoid tolls? It could also be the total time. It could also be the total mileage. But what is something that they all have in common if it's a good program? They all get you to the same place. They all have the same start and the same end, but they get you there potentially different ways. And you can choose which one of these ways do you like. And so these different approaches could have lots of things in common, such as starting point and ending point, but they could also have a lot of things that are different. Right now, this is just proving that given a permutation, we can write it as a product of transpositions. Later, we'll say, imagine there are 2 different decompositions. What can we say must be true about both of these decompositions? Do they have some properties in common? We know they both have to equal the permutation pi, but what other properties do they have in common? So I claim without loss of generality, we may assume pi is a cycle. Why can we assume pi is a cycle? Instead of considering a general permutation, why can I assume it's enough to prove it in the special case when pi is a cycle? Yeah, we just proved a moment ago that every permutation can be written as a product of cycles. And so if I can prove that one permutation, that one cycle can be decomposed into a product of transpositions, then I can do this for each one of them. So it's enough to assume that I have a cycle. And without loss of generality, I might as well assume my cycle sends 1, 2 through n to 2, 3, 4, ... and 1. You know, I can renumber things so that 1 goes to 2, 2 goes to 3 if I have a cycle. So I'm going to prove it by the method of divine inspiration. The way the method of divine inspiration works is you write down the right answer and then you show that it's the correct answer. What's the problem with the method of divine inspiration? Yeah, you need to be divinely inspired, and you're not always divinely inspired. So the idea is to try to come up with a procedure that will work, that you can then apply in other situations. And again, I care more about the thought process than the result. So let me start off with, I want to write things as a product of transpositions. Let me start off with tau of 1, 2. So this sends 1 to 2, and it sends 2 to 1. Does that equal my cycle? No. Does it have anything good about it? I sent 1 to 2. So let's try to fix this by now putting something in that's going to keep 1 going to 2, but will send 2 to 3. Well, I know tau 1, 2 sends 1 to 2. It sends 2 to 1. So I want something that sends 1 to 3. So can you give me a transposition that sends 1 to 3? Yeah, tau 1, 3. So let me try tau 1, 3. And if I now look at this, tau 1, 2 sends 1 to 2. Tau 1, 3 it does nothing to 2. So this is going to still send 1 to 2. Tau 1, 2 sends 2 to 1. Tau 1, 3 sends 1 to 3. This sends 2 to 3. And now tau 1, 2 does nothing to 3. Tau 1, 3 sends 3 to 1. So this sends 3 to 1. So this does not give us what we want, but it's better than tau 1, 2. I've now got 1 going to 2 and 2 going to 3. What should I try next? Yeah, tau 1, 4. And if I now do tau 1, 4, we will see 1 goes to 2, 2 goes to 3, 3 goes to 1, 1 goes to 4, so it goes to 4. And now 4 goes to 1. And so we just keep going. What's the last one? It should be tau 1. What would you say the last one should be? N. And so here is something that works. So again, we started off with tau 1, 2, and then we decided to correct it. You know, it sent 1 to 2, which was great. It didn't send 2 to the right thing. So we then put something in that fixed that without affecting the fact that 1 went to the right thing. And we kept fixing it one thing at a time. And at the end of the day, everything worked out. Note, of course, we could also do tau 2 goes to 3, 2 goes to 4, ... Tau 2 goes to n, tau, how would we keep going? We go 2 goes to 1, I think. I think that would be the last one we would do. And this would be another decomposition. Now notice in this, the two have the same length. Are you always going to have the same length? What do you think? So I can write E as tau12, tau12. I could also write E as tau12, tau34, tau12, tau34. So as soon as I do something like this, you see that I can actually play some games. And so this is enough to prove that they're not always going to have the same length. Oh, well. But what do you notice about these lengths? If I simplify them, yes, but again, I can do lots of things like this where I'm not going to be able to simplify this unless I do the whole multiplication. But they have to simplify to the same permutation. And you could say, given any permutation, I could look at maybe the minimal product of transpositions. You're just like, I might want the fastest route. And the fastest route could be either defined in terms of time or distance. I could say, take the permutation that has the fewest number of transpositions. But it's not at all clear if I look at the two ones I have over here, they both have the same length. But the first one is tau1 something. I never have a tau23 or a tau24 in the second. So they're not going to have the same elements. But what can you say about the length? What do you notice about the length of these two different decompositions for E? They're both even. And so it turns out that the theorem is that if we can write pi as a product of transpositions in two different ways, then the number of terms in the products are either both even or both odd. Or another way of saying it is they have the same parity mod 2. So I can't have an odd and I can't have an even. They both have to be odd or they both have to be even. It is possible that we could have more than one decomposition. So when I write this theorem is just saying that K is congruent to L mod 2. It doesn't actually say that there have to be at least two different decompositions. We just showed a moment ago that there are at least two different decompositions. As soon as I have two elements, I can throw in multiple ways of writing the identity. So this is a non-trivial theorem. So the proof of this uses an interesting polynomial called D, and it's defined as the product of all pairs xi minus xj, where the index j is less than I, and the indices are drawn from y to n. Does this remind you of anything we've seen recently? Have we seen anything like this recently? Yeah, these are the van der Waals matrices. There was a reason I introduced these. It's a little bit different than how we did them. Is they're starting off at 1, we started off at 0. I did this to somewhat alert you to the fact that you have to be careful when you're looking things up as to what notation, what conventions do they use. If you've done multivariable calculus, spherical coordinates is big. Is the angle coming down from the z-axis, is it beta or is it phi? Mathematicians prefer phi, physicists often use theta. There's good reasons for both. You just have to be aware of which source you're looking at. Let's let pi be the permutation, 1, 2, 3 goes to 3, 2, 1. So this is the same as the transposition 1, 3. Let's see what pi does to this polynomial. So I will take pi and I will apply it to d x1, x2, x3. Well, before I apply pi, let's just write down what d of x1, x2, x3 is. That's going to be, I always have the higher index first. It's going to be x3 minus x1 plus u, x3 minus x2, x2 minus x1. And now if I apply pi to d of x1, x2, x3, that's going to be d of x pi 1, x pi 2, x pi 3. That's going to be d of x3, x2, x1. So basically, wherever I had an x3, I replace it now with x1. Wherever I have an x1, I replace it with an x3. And if I had an x2, I leave it alone. So when I'm looking at what the polynomial is, the x2s are unchanged. And now all the x1s become x3s. And all the x3s become x1s. And I'll switch things over here just to try to make things a little bit easier to read. And so I'll color code things, x3, x3, and I'll color code the x1s to be green. Oh, I have a typo here. This should have been x1. Okay. Do I have the same factors more or less? Yeah, for each of these, everything is changed by -1. So before I had x2 minus x1, now I have x1 minus x3. So this is just going to be -1 cubed d x1, x2, x3, or just negative d of x1, x2, x3. The impact of the permutation, pi, which is just tau 1, 3, which is just switching 1 and 3, is to change the sign of d. And you could ask, what would happen if I applied a different permutation other than just a transposition? Why do you think I only cared about the effect of a transposition? Yeah, because I can write any permutation as a product of cycles. I can write any cycles as a product of transpositions. So any permutation is just a product of transpositions. So if I can figure out what a transposition does, I can figure out what a product of transpositions does. And so a simple calculation shows that the square of d is equal to the following. And if you think about what was going on, is if we squared d, let's say we had something like, x3 minus x2, x3 minus x2. That's what we get when we're squaring things in d. But notice when we look at the product now, before when we wrote things for d, we always wrote things for d so that the smaller index was first. So the large index was first, the small index was second. xi minus xj with I greater than j. When you look at how we're writing things when we square it, we're looking at all distinct pairs I and j. So I would have an x3 minus an x2 and an x2 minus an x3. What's the difference? Well, if I have x3 minus x2, x3 minus x2, if I want to write this as x3 minus x2 times x2 minus x3, what's the cost? The cost is a negative sign. And so when I square it, the number of negative signs I have is going to just be equal to the number of terms. So if I go back a page, how many terms do we have in the product? Okay, and in general, how many terms do we have? We look at all the distinct pairs I and j between 1 and n. So how many distinct pairs do we have? It's n choose 2. So the number of terms is n choose 2, which is n minus 1 over 2 or n squared minus n over 2. And so when you look at what's going on over here, this is just the number of terms in D. Each gives a factor of minus 1. And that's where this comes from. And so now, if I look at pi of D squared, x1 through xn, that would be D squared x pi 1 dot 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 x pi n. What should that equal? If I shuffle the order of the variables, what should the change be? Well, look at D squared. It's the product over all distinct pairs I and j. If I shuffle the order, have I changed the product? No, I've just changed the order in which I write things. This is still going to just be D squared of x1 through xn. For example, you can go through and see what would happen if I have n equals 3, and let's take pi is a cycle. 1, 2, 3 goes to 2, 3, 1. So I would have negative 1 to the 3 squared minus 3 over 2. 9 minus 3 is 6 divided by 2 is 3. So it would be negative 1 cubed. And then I would have the product over all I and j not equal. So I would have x3 minus x1, x1 minus x3, x3 minus x2, x2 minus x3, x2 minus x1, x1 minus x3. And now I apply pi. I would still have a negative 1 cubed. And now I send 1 to 2. So the first factor is going to just become x3 minus x2. The next factor is going to become, I send 1 to 2, 2 to 3, 3 to 1. I'm not doing the transposition. So x3 goes to x1, x1 goes to x2. So I get x1 minus x2. The next factor, x1 becomes x2, x3 becomes x1. The next factor, x3 becomes x1, x2 becomes x3. The next factor, x2 becomes x3, x3 becomes x1. The next factor, x2 becomes x3, x1 becomes x2. And the last factor, x1 becomes x2, x3 becomes x1. And now we just match things. x3 minus x1, x3 minus x1. And then I have x1 minus x3, x1 minus x3. x3 minus x2, x3 minus x2. x2 minus x3. Did I make a mistake somewhere? I must have been, so the last one. Okay, so the second one was x1 goes to x2, x3 goes to, I wrote x1 minus x3 twice. The last one should be x2 minus x3. It's a typo, sorry. And so then that one should then be x3 minus x1. So did I do everything? So x2 minus x3, where am I making my mistake? Okay, I've got x2 minus x3 twice again. I made a mistake in both parts. Both indices were wrong. It's x2 minus x1. There you go. And now when I fix that, then it should become x3 minus x2. Good. So x3 minus x2 . Oh, but I wrote this in the wrong order. All right, take 4. All right. So it's x1 minus x2. I just wrote the stuff in the wrong order, that one factor. So then x1 goes to x3, and then x2. No, I'm sorry, x1 goes to x2, and then x2 goes to x3. Okay, there we go. And now it works out. And that's 4. Then the next one is x2 minus x1. I've got an x2 minus x1, that's 5. And then x1 minus x2 is 6. So all the factors match perfectly. All right. I made, unfortunately, several typos in the last factor, but it all matched up. So when I applied pi to d squared, I got back d squared. And it makes sense because if you look at it, I've got the product over all distinct pairs. And so when I apply any permutation, I'm not really changing the product. I'm just changing the order in which I write the factors. Why don't I want to allow an I to equal a j? What would happen if an I equals a j? Yeah, everything is 0, and I'm not going to get anything from analyzing it. So now we can use this to prove that the number of transpositions in any decomposition is either always even or always odd for a given permutation. And what we just noticed is that the polynomial d squared is invariant whenever we apply any permutation pi. So pi of d squared is equal to d squared. But pi of d squared is just pi of d times pi of d. So what should this remind you of? Pi of d squared is pi of d, pi of d. What does this kind of remind you of? Have we seen something like this before? The pi of a product is the product of the pi's. What does this remind you of? Yeah, it reminds you of a group homomorphism. So we know that pi of d squared is the square of pi of d. So this tells us that pi of d is either plus or minus d. That's the only way that it can square to. So we know pi of d is equal to d times d. And so we get pi of d is plus or minus d. So we just have to figure out which is it. And all we have to do is figure out for transposition. And the claim is if we take any transposition and apply it to d, we're going to get back negative d. But the transposition just changes things by multiplying by -1. So what we're going to do is we're going to apply a transposition to our product. And so what we're going to do is we're going to just look at how many times does it change a factor. So if we looked at what went on for the example we had earlier, it turns out that the transposition impacted all 3 of our factors here. And it was going to give us a -1 cubed. I don't care how many factors it impacts. I only care how many factors does it impact up to a multiple of 2. And so the book does a really nice job of writing things down. So let's imagine we have the transposition, tau AB with A greater than B. And we want to see, what does this do to the different factors? A lot of times it does nothing. So it only impacts xi minus xj if at least one of I and j is in the interval AB. If If xi and xj come from indices I and j that aren't in AB, then this has no impact. One possibility is that both I and j are in this interval. The only way that can happen is if we have the factor xa minus xb. Because now we're looking at D, and when we look at D, we write things with the large index first. So if they're both in the interval AB, the only way that can happen is the factor xa minus xb. Both in AB, that's the factor xa minus xb. Changes to xb minus xa costs us a minus sign. And now we can look at what happens in general. So if I have xa minus xj, xj minus xa, with j greater than a. If I move a down to b, so again, my largest number is on the left, my smallest number is on the right. If I move a to b, is it going to change xj minus xa? It's not going to cost me a minus sign to keep the larger index first. So there'll be no change there. Similarly, if I have xb minus xj and I move b to a, that's not going to change the stuff there. So I only have to worry about when my index is between a and b. So one of my indices has to be a or b, and the other one has to be between a and b. If it's after a or before b, it's not going to change anything. It's going to be paired off with something else. So then there's a really nice table which you should have read, where we look at all the different factors of D. We look at what happens when we apply tau, and we look at whether or not there's a flip. And we see that in many cases, there's no flip, that it's just matched with something else. There's the case of xa minus xb, which has one flip. What kind of number is this? What kind of number is 1? Well, this problem is all about proving things about parity. So what do you think I care about this number? It's odd. So, because the writer of this book is a gifted mathematician, he's giving a full proof. He's calculating exactly how many flips do we have in each situation. So whenever we have a factor of xa minus xi with I between a and b, we're going to get a flip. It's going to become xb minus xi. That's actually balanced. It can be paired with all the flips from xi minus xb with I between a and b. So he calculates that the number of such factors is a minus b minus I in both. I don't care how many there are. All I need to know what's true about these two numbers. It's the same. He calculates exactly what the same number is, but I can just match things in pairs. And so I only need to calculate the number of sign flips as to is it even or odd. And so when you write things down, we have all the factors that don't involve an A or B. Those are unchanged. We have the factor xa minus xb, which has a sign change. And then we have the two other ones that are going to be matched in pairs. And each one of them is going to have a sign change. So the number of sign changes is going to be odd. And so again, we do have it's 1 plus a minus b minus 1 plus a minus b minus 1. But as long as I have something like a minus b minus 1 doubled, all I need to know is anything that's an integer that's doubled is even. If by any random chance you happen to have taken a class in operations research and happen to have seen a proof on some of the fixed point theorems and triangles and whatnot, this might remind you of something like that, where we only need to detect things up to parity. Okay, so from this, we can get a lot of interesting results. One thing I guess that's worth mentioning is we now know that any transposition, that any permutation can be written as a product of transpositions. There is a situation where we use permutations, and your permutations arise in determinants. I will just take a quick digression here because this is sadly not covered in a lot of linear algebra classes. There's a lot of tricks in mathematics that don't always work, but sometimes work, and they're good mnemonics. This was a mnemonic that was taught when I was young. It doesn't seem to be as popular nowadays. If I give you the matrix, let's say 1, 2, 0, 3, 4, 1, 2, 3, 2, and I want to find its determinant. Have you seen the trick that you just write down the first two columns again? This is a really good trick to find the determinants of 3 by 3 matrices. It doesn't work for higher. You then go diagonally down like this and you multiply. So 1 times 4 times 2 is 8, 2 times 1 times 2 is 4, 0 times 3 times 3 is 0. And these all get a plus sign. And then the other one is you go the other way. That's going to be a 0. 3 times 1 is 3. 2 times 3 times 2 is 12. And these all get a minus sign. And so the determinant is going to be 8 plus 4 plus 0 minus 0 plus 3 plus 12. So this is a really nice trick to find the determinant of a 3 by 3 matrix. It sadly does not work for higher. You could actually get this to work for a 2 by 2 matrix. If I gave you a 2 by 2 matrix A, B, C, D, just put in a bunch of zeros, right? And do it like this, and that will work. I'm sorry? Really? Right. I mean, this is a way to just show that it actually does reduce to that formula. Yes. I would just do AD minus BC. Yes. If you truly wanted to, you could bump up a 2 by 2 matrix like this and have this work. This is, I think, faster than doing the Gauss elimination and whatnot to try to calculate the determinant. It does not work in higher. But what you notice is we have products of 3 elements. And in the determinant, if you have an n by n matrix, you have n factorial products that you have to then add and subtract. And each one gets a plus or minus sign. This is your expansion by minus. And you have to remember, where do you get the signs? The signs actually come from the permutations. When you're expanding out the determinant, the sign in expanding out the determinant, it all comes down to these products of permutations. Is it an even or is it an odd number? Just some language as to where things go. So we have a beautiful theorem due to Cayley. Every group is isomorphic to a subgroup of some symmetric group. And then if G is a finite group of order n, it's isomorphic to a subgroup of Sn factorial. How many elements are in Sn factorial? Yes. No, note, n factorial factorial is not actually equal to n factorial factorial. N factorial factorial is actually n times n minus 2, n minus 4, dot, 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 all the way down to either 3 times 1 if it's odd, or 4 times 2 if it's even. This is just how we've defined the double factorial. The double factorial is not the factorial of the factorial. This turns out to have lots of implications in combinatorics. Sn factorial is a very large group, but no matter what finite group you give me of order n, it lives inside Sn factorial. A group G is a simple group if its only normal subgroups are G and E. And recall, H is normal in G, and we write H with a triangle like this G, if for all G in G, what's true? So what does it mean for a group to be normal? Yep. So there's two different ways you can write it. GH, G inverse equals H, or GH equals HG. We're not saying that multiplication is commutative, but we're saying if you take the subgroup H and you multiply on the left by G, or you multiply on the right by G, you get the same set of elements. Maybe in a different order, but you get the same set of elements. This is what it means to be normal. Every group has two normal subgroups, itself and the identity. This is not a big deal, right? We call these the trivial subgroups. Are they always distinct? I'm sorry? Right. So as long as you have at least two elements, they're distinct. If your group is only the identity, they're actually the same. So I have to be careful. I can't say every group has two trivial subgroups. I can say every group always has the trivial subgroups itself and the identity, which may not be distinct. It turns out that these are trivially normal. Well, clearly G is going to be normal because anything times G, you just get back G. And clearly the identity is a normal subgroup because everything commutes with the identity. So it's really not that impressive to find a normal subgroup of a group. This is basically just to see who's awake right now. Just writing down G or the identity is an example. We say a group is simple if its only normal subgroups are the trivial ones. So for example, let's say I give you G is the set E, A squared, A cubed, A to the fourth, A to the fifth, A to the sixth. It's cyclic, it's generated by A with A to the seventh is the identity. So this is a cyclic group of order 7. If I want to find a normal subgroup of G, what's the first thing I should look for? Before looking for a normal subgroup, I should look for a subgroup. No. So what are the subgroups of G? So what are the possible subgroups of G? Okay, but if I look at A squared, I would have A squared, A to the fourth, A to the sixth, A to the eighth. A to the eighth is the same as A. So actually, if I look at what's generated by A squared, I actually just get back G. So what are the subgroups of G? I'm sorry? Okay, so how do you prove that it's simple? Okay. Lagrange's theorem. By Lagrange, the order of H divides the order of G, and only divisors of 7 are 1 and 7. So a cyclic group with a prime number of elements is simple. So in some sense, simple groups are building blocks in group theory. And so you should be at least aware of the following definition. So if we have a finite group, we can create what's called a composition series, which is a sequence of groups. Each one is properly contained in the previous. We start at G, we end at the identity. And as we go down, each group GI plus 1 is normal in GI. And if we look at the quotient group GI mod GI plus 1, that's a simple group. And if in addition, these quotients are also abelian, then we say the group is solvable. Whenever you see language and notation, you should always ask, why are we choosing this notation? This language comes back from trying to solve polynomials and write down formulas for the roots of a polynomial in terms of the coefficients. So if you're interested in stuff like this, this is then done in greater detail in Galois theory, where it's, when can we write down solutions? And it turns out we have the quadratic formula. You should be able to prove that right now. You should either be able to complete the square, or you can use the method of divine inspiration because you know the quadratic formula. Look at x minus the first root times x minus the second root, expand that out, multiply by a, and show that you get your polynomial. There is a formula for the cubic and its roots. There is a formula for the quartic and its roots. There is no formula for the roots of a general degree 5 and higher polynomial. And that's where this language comes from. So it's natural to ask, what are the possible simple groups? So it turns out that there is a complete classification of simple groups. One of my professors at Yale, Professor Feit, was one of the people who is credited with finishing the proof of this. This is the Feit-Thompson theorem. So if G is a finite simple group, these are the possibilities. A cyclic group of prime order, good, we saw that. The alternating group AN with n greater than or equal to 5. And so over here, I didn't really say too much about theorem 2.9. The alternating group, which you should have read, is this is the set of all permutations with an even number of elements of transpositions. So if I have an even number of transpositions and I multiply by an even number of transpositions, do I have an even number of transpositions? If I have an odd number of transpositions and I multiply by an odd number of transpositions, do I have an odd number of transpositions? So if I have 3 transpositions and then I multiply by something with 3 transpositions, how many transpositions do I have? I'm just adding, so I would have an even number. So if I take 2 permutations that have an odd number of transpositions and I multiply them together, I end up with an even number. So having an odd number of permutations, that's not closed under composition, but having an even number is closed. So you can show that the alternating group of the symmetric group deserves the name alternating group. It is a group. I could look at all the permutations with an even number. I can look at all the permutations with an odd number of transpositions. I know you give me any permutation, it's in either one or the other. Because we know that the number of transpositions, no matter how you decompose it, it's either always even or always odd. And it turns out that the alternating group is a simple group. It's a long calculation. It's not worth doing in class. I strongly urge you to just go through the algebra in the book and just see. It's interesting. You need to have at least 5 elements to show that it's simple. For smaller ones, it's not the case. You have some freedom going around. And so the first 2 examples of simple groups we've seen, the next 2 are far more involved. And it's way beyond what we can do in this class. But there is a classification. It's nice to know that it exists. There's also a structure theorem or classification for finite abelian groups. So if we assume a group is abelian, then things are a lot easier because everything is normal. Because if the group is abelian, then GH is clearly HG because everything commutes. And so it turns out we can write down explicitly what you would get if you have a abelian group. And the list is much shorter in terms of what happens there. So this is a good place to stop. I will just end the video with just putting back up. Do not cheat. Do not go online. You can talk to each other, but try to think, what is your best strategy? As mathematicians, can you do better than a 1 in 10 to the 30th chance, roughly, of winning? Or is the warden just having fun with you and there's really nothing you can do? All right, this is a good place to stop.